All right, here we are going to do a proof. We are going to show that the derivative of an even function is an odd function. And we'll be using the definition of derivative to do this. So check this out. First, let's write down pf for proof. And then, of course, we need a function to start with. So let's just say, let f be our function. And what kind of function do we need? An even one, right? So let f be an even function. And what does even function do? Well, this means when we have f, if we put negative x inside, the negative doesn't matter. This right here will just give us f of x. So that's the property of a function being even. And technically right here, we should say something like for all x in the domain of the function f. So that's what we have. And what do we want to achieve though? We want to show the derivative is odd. So let's go ahead and write this down. We will show the derivative, which is just f prime. But if you want to show that's odd, what we need to do is, if the input is negative x, if this is odd, that means we can put a negative on the outside. So we want to have negative f prime of x. And I think this is super important. You should always write down what we have and then what we are trying to do. So that way you know exactly how to start with the question. Because now it's more clear that let's just start from the left hand side. And then just use the definition of derivative, and hopefully we can end up with the right hand side. And of course, this right here is going to help us out. So here we go. If we look at f prime of negative x, by the definition of derivative, this right here is just equal to the limit as h approaching 0. And then the definition says we will have the f, and then the input right here, which is negative x, we add h to it, and then minus f of that input, and all divided by h. So that's good. This is a very good start. What can we do right here? Well, because f is even, so that means we can get rid of this negative. But this is negative x plus h. We cannot get rid of this negative yet. What do we have to do first? We have to factor it out, because it's negative of an input, right? So it's not like an input plus something else. So right here, let's just go ahead and factor out that negative. So we have the limit as h approaching 0. First, we have f of negative, and then the inside is x minus h, and then minus f of negative x. So I haven't got rid of the negative yet because I want to do them together right now. This right here is equal to the limit as h approaching 0. This negative doesn't matter, so we just write down f of the input, which is x minus h, like this part only, and then minus f of just x. And right here you can mention that since, well, because f is even, so that's how we were able to get rid of these two negatives. And of course, we still have this all divided by h. Now, is this the definition of derivative? Is this f prime of x? Almost, right? Because we want to have a plus here, right? X plus something. This is a minus. What do we do? Well, in this case, let's just do a change of variables to make things super clear. So right here, I'm going to say let k be negative h. And the reason is because when we have this limit, if we do a change of variable, well, the output will still be the derivative if it's the same structure of the definition of derivative. And then we really want to see the x plus that quantity, which is approaching 0, not subtracting, all right? And yeah, and then just don't let this variable bother you. This is the so-called dummy variable. Earlier right here, we could have used k already. It's still true. You can use j, you can use t, doesn't really matter. Right now, with this substitution, we are going to get what? Let's see. This is the limit. Well, h is approaching 0. You can put 0 in here. That means k is also 0. So that means k will also be approaching 0. That's good. And then we will have f of x. But negative h is the same as positive k. So we can just say, let's add k to it, and then minus f of x. And here we have h. Well, what do we do? Well, if k is equal to negative h, that means h is equal to negative k. Very nice. Yeah? Okay, so what exactly does this help us? Now, if you look at the structure, this is just like the definition of derivative, but this is negative. But don't worry, because we can put a negative at the front. So we have this being equal to negative, and then we have the rest is the limit as k going to 0, and then we have f of x plus k minus f of x all divided by k. And then the negative stays, but this right here, as I said earlier, if you look at the structure of it, this right here is just nicely equal to the definition of derivative, and the input is just x. And that's exactly what we want to achieve. So we are done. Therefore, when f is even, we know that its derivative will be odd. And since this is a proof, what we do is we draw a box right here and we shade this in, meaning that the proof is done. And in fact, you can also show if the original function is odd, if you replace this with odd, then you can show that the derivative is even by doing the same thing. So that will be the practice for you guys, right? That's it.